Hello. So all are there?
Yes, sir. Good morning.
Yeah, good morning. Okay, so today I'm going to start the stability of slopes. So this is another chapter of the stress path. So before I begin this chapter, if anybody has any question on all the previous classes, so you are most welcome. So anybody wish to ask any question or get clarify whatever the questions we have in your mind.
Sir,
Yeah.
sir, in undrained test, consolidation
Yes.
undrained test,
Yes.
uh, there is information given as pore water. So we calculate both effective stress and total stress, right?
Correct.
And we'll draw two lines, two failure envelopes corresponding to total and effective.
Correct.
So if there's a cell pressure given, different cell pressure, and asked to
Okay.
find out the deviator pressure.
Okay.
So which failure envelope would we consider, like effective or total? For which one we consider?
If you are asking to determine the deviatoric stress,
Yes, sir. So for a
so
different cell pressure.
for a different cell pressure.
Yes, sir. Like, should we consider the effective envelope, effective stress envelope, or total stress envelope for calculating this value?
In fact, you can follow any of the path, or sometimes
So,
you have to, actually there is no specific rule for this one because
so but
depending upon the data.
for one question I was solving, the answer was based on the total stress. So that's
Ah,
my question
that,
actually.
yeah, that's what I'm saying now. So it depends upon the kind of data that has been given. So, in fact, when you talk about determination of total, effective, and pore water pressure, so everything is interlinked. Right? Sometimes we may have to use only the total stress analysis, sometimes only the effective stress, or sometimes you have to use the combined data of total and effective. So everything is interlinked. There is no independency.
So if someone asks for this, so we'd give both the answers then, like for these both conditions.
Yeah, we can say that. So there is no specific means unless otherwise if data is known, there is no specific thing is like you need to follow the effective stress or total stress path.
Sir, or I will share the question to you. Meanwhile, if you have any time, you please look at it and just mention me which one you should consider.
Okay, no problem.
Yes, sir.
No issue.
Thank you.
Yeah, I'm sorry. So I was not there for your tutorial because I had to go for JEE duty on last Saturday. So Saturday, Sunday, I was totally busy. So with JEE duty. So hope it was fruitful. I don't know whether. So which otherwise today I can take up the stability of the slopes. So shall I start or do you still want to ask a couple of questions?
Sir, in last class we were discussing about direct shear test. That was not
Okay.
completed.
Acha, actually that is same stress path only. It is not of that much importance.
Okay.
In fact, I have given more informative example on the same day so that I got it. So I skipped this direct shear.
Okay.
It was on Mohar circuit only. There was no problem.
Okay, sir.
Okay. So when is your mid exam going to start?
From 7.
So 7th of October.
7th of October. Okay. So then how many classes do we have? I have to see whether I could able to finish it up the stability of the slopes. So this week we have a 4. So in effect, how many classes we have? So today is 29, so 34 classes. So 7th means next Wednesday. Oh, so next Tuesday I can't able to take. So I think only 4 classes I could able to take this week.
Sir, 3.
Today 2 plus tomorrow and Friday.
Friday is not possible, no?
Why?
In October, sir.
Friday?
Friday is a holiday. Gandhi's birthday.
Oh. Acha. So only 3 classes.
So
No,
next
but
Tuesday,
next Tuesday on 6th we have 2 classes.
On 6th, yeah.
Yeah.
6th we can have 2 classes.
five classes, sir.
Okay, no problem.
So 5 classes, I guess, total.
Total 5.
Yes, sir.
Okay, so let me see how much I could able to cover. Okay, so we for your mid-semester examination, whatever the syllabus and did they inform about how many marks it should be and how much time? So do you have any kind of information?
For 2 hours it will be.
Means have you received confirmative email or
Yes, sir.
it
We
was
have
just
got the date sheet and the timings.
okay? And how many for how many number of marks?
So this we don't know.
Achha.
So
In
in maths
maths,
that is 40
maths
marks.
it was 40 marks. Sir was telling.
Maximum for 40 marks.
Maths in maths, sir told us about 40 marks.
Okay. 40, 50, 40. Okay. So that
Sir,
means
did you tell
what?
syllabus because your voice broke off?
Yeah.
Hello.
See the maximum marks to be covered for mid-semester examination is 40, and teaching assignment, that is my assessment, is 20. Then end exam is another 40. So probably your end exam will be also on online for about 2 hours.
And so what is the syllabus for mid-sem?
Whatever I'm going to cover up to tomorrow.
Okay, sir.
So although we have a class on Tuesday, but Wednesday your exams are going to start. So I don't know whether Tuesday you could able to join for a class or not. Just tell me, are you able to join for a next Tuesday class that is 2 hours, or shall I compensate after the mid-sem?
Yes, sir, that would be better.
Yes, sir. That will be better.
Or sometime in this week only, some additional class.
Sir, after medicine will be okay.
You want after the mid-sem?
Yes, sir.
Sir, on Saturday we are having class test, so Saturday is not possible.
Saturday have a class test.
Yes, sir, 2 class tests.
Which subject?
One is for geotechnical lab and second one for computational geomechanics.
Acha. Okay, fine then. So
So,
I will.
sir, on Friday itself you can take the class. It's no problem, only 1 hour, right?
Yeah, only 1 hour.
So Friday we can take the class. It's no problem.
Okay, fine then. So then, in fact, I can take 2 hours, then 9 to 11 Friday. So if you don't have any problem, so I can cover up 2 classes on that day.
Lockdown only, sir.
Is it okay then? So Friday I will schedule instead of 9 to 11, 10 to 12 better. So I will continue 1 more hour, 10 to 12 this Friday. Okay, so that's final.
Okay, sir.
Yeah, fine, good. So let me start the stability of the slopes. So in fact, you got a wonderful introduction during your undergraduation program. So what is the slope stability? And it's not coming. It's not coming. For where it is coming? Okay. Okay, so hopefully the slope stability chapter has been covered for everyone. But anyhow, let me take a retour of this entire chapter. So starting from everything, so that this becomes kind of a recapitulation of the fundamentals of the slope stability, as well as so addressing all other remaining methods which you did not come across. So I'm sure so everybody might have dealt with the infinite slopes. Okay, so basically when you talk about the slope stability, you should be aware of the fundamental distinction between the two terms. One is slope stability, next is a landslide. So landslide is a general terminology, so nothing to do with the slope stability. But a landslide can occur, it is an external name. Landslide can occur so only when there is a slope instable. Doesn't matter whether this slope is an infinite slope or a finite slope, so which is immaterial. But since we are dealing with the soil, so we, instead of calling this as a landslide, so we call this as a slope stability, because we purely deal with only technical aspect of why and how slope is going to fail. So if anybody talking about the slope stability, a very simple way of understanding this one is a large or a definite volume of the soil chunk is getting displaced from one place to the another place. So this is the fundamental meaning of your landslide. Certain mass of the soil or the land is going to be displaced from one location to another location. It involves so shear stress and shear strength of the soil. Shear stress and shear strength of the soil. So there are a variety of conditions under which so the slope stability can occur or the slope can fail. So this is an infinite slope where you can see certain chunk of the soil mass is sliding away on hard surface. So it is infinite slope because the length is unknown. It can happen over any indefinite length of the soil mass. But usually the failure surface or the loose strata does exist on a firm strata, but the thickness of the loose strata is very shallow or very thin. It's not that much. Okay. On the other hand, so when you construct any embankment or earthen dam, so when the slope is going to fail, here we know the complete geometry of this particular embankment or the pavement. So therefore it is called as a finite slope, where the length and everything is known, that is called as a finite. Where the geometry is unknown, that is called as infinite slope. One of the best example of infinite slope is your landslides on hilly area, and any other slope failure is called as a finite slope. So here we can see one fundamental thing that you need to understand the distinction between the shear stress and the shear strength. So the shear stress and the shear strength. So these are the two terminology you need to understand. For example, for better understanding, let us look at the cross section of this earthen dam. Okay, so here, so there is a ground surface and there is an inclined surface. This is called as the face of the slope, and on top of it there is a berm or the top surface, whatever you call it as. Then this is the predictable, the slope all along which there is a possibility of the development of the failure plane. Now if you look at, there are two bodies. One is body A, B and C, which is above the failure plane, and the same soil mass, so which is below the failure plane. So some above the failure plane and some soil mass below the failure plane. So the soil mass which is separating above and below is called as a failure plane. Which is causing failure. This mass is called as a shear stress mass, or the mass which is causing a shear stress in the soil mass. While on the other hand, the resistance that is developing all along the failure surface from A to C, which is immaterial whether the failure plane is a circular or rotation or log spiral, immaterial. So the kind of the shear strength that developing all along the failure plane AC, this is arc length AC, to resist the sliding mass of W, that is called as the shear strength. Shear strength always develops in the in situ soil. Shear stress always caused by the gravitational force. Gravitational force. In fact, the gravitational force or the shear stress development can be accelerated or triggered by another natural forces, which includes one of them is a seepage. One of them is a seepage, or another is uh, the sudden increase in weight of the soil mass. That is called as a sudden drawdown, sudden increase in soil mass, or earthquake. So this is some kind of an external perturbation. External perturbation. So in all the cases you have to understand, when I talk about the weight of the soil which is causing shear stress on the soil mass, it has two components, vertical as well as in horizontal. Or for that matter, when you talk about any slope stability, you will be having two components. One is in horizontal, next is in vertical. So vertical means the weight of the soil sample, while the other elements cause the horizontal forces, maybe seepage or maybe earthquake. So this further aggravates the problem and thereby triggers the slope failure. So this is a very simple understanding how the landslide that can accentuate in case of the natural slopes. Here you can see, so this is a natural slope where there were some layers or some layers of the soil which could able to hold the water. So this is one layer and this is another layer. This is for better understanding. This may not be exactly mimicking the nature, but try to understand. But this is what exactly happens in the nature. So this is a mature slope where one can expect that there is no possibility of the slope failure, landslide. Since we are talking about the natural slope, we can assume that there is no landslide. But if you look at carefully, this is the perfect shape of any failure or landslide, slow failure or landslide. But what happens in the due course of time? So maybe hundreds of years, maybe thousands of years, what possibly could happen? What happens is there is a possibility of the erosion starts. So this is because of the continuous or the cyclic nature of the nature. So summer, winter, summer, winter, rainy season, summer, winter, rainy season. So because of this cyclic motion, so the shape of the curve, which was initially maintained, will be undergone the modification. So because of the natural process, one of the natural processes, say erosion. Because of the erosion, here you can see initially this was a particular curved shape, but this curved was deformed into another curved shape, causing so imbalance in the original shape. When there is an imbalance, so it causes imbalance in some kind of a soil mass. Here you can see, so the erosion caused some kind of imbalance in certain soil chunk, So this become imbalanced. Whenever this is becoming an imbalanced, it always try to move or slide on the inclined plane. So that's what normally we call as the landslide. But the the factor which is causing the landslide is slope instability. Slope instability. So you can see. So another fundamental reasons how the initially maintained natural slope is undergoing changes and thereby causing the landslides or different phenomena. So there could be landslide, or there could be mud flow, or there could be debris flow, so on and so forth. So this is a real life picture. So how the slope has undergone some kind of a landslide. So this is the perfect example. So this is some important information about the landslides which we should aware. So when you talk about any soil mass, its consistency changes from initially hard to the viscous behavior, that is the slurry state. This is the transformation that one can expect. So let us try to understand what are the different what do you call different states of the soil mass. So this to be enough consistency with the highest amount of water content. It should flow under its own gravity. Flow continues as long as shear stress is maintained. So normally viscous flow occurs in case of water or slurries or mud flows. Then plastic behavior involved in many types of the slope failure, especially in clayey soils. So a typical example is between from plastic limit to the liquid limit. If the shear stress is less than yield stress of the regolith, no deformation occurs. If the shear stress is equals to yield stress, then the plastic body deforms. So again, shear stress means the kind of a force that is causing instability in the soil mass. Then elastic and brittle behavior. Elastic, where recovery occurs when stress release takes place, and brittle, so where the reaction to the stress is a fraction. So this is a very well known to you all, but just a recapitulation. And soil with high concentration of montmorillonite clays are liable to plastic and liquid behavior. So this is what we understood also, due to the fact that the clay lattice can absorb more water than the other clays such as kaolinite. So wherever there is a montmorillonite, so the plasticity index is so high, and there are if you look at carefully on the YouTube, there are several kinds of the failures where you can see huge chunk of the soil mass is landslided. So because of a very thin layer of presence of the highly plastic material, there are several examples. So this is what exactly happens. You can, if you draw a strain rate versus stress for different materials, so this is what the flow happens. So the viscous flow, for example, if you take the viscous flow, as the stress or the strain increases, conversely there is an increase. So if you increase the strain rate, there is an increase in the stress. However, there is a proportionality between the stress versus strain. Suppose if you look at a perfect plastic material, there is no recovery is possible at all. So it could able to take only one small amount of the load. Okay. So the moment you start applying the load, it undergoes the deformation. So there is another law. This is valid for the ice. So we don't need to discuss this. But this is what the difference between if the material is behaving like a viscous or if the material is behaving like a plastic. So this is how their stress strain graphs probably looks like. And depending upon viscous flow or plasticity, so that all the terminology comes based on this viscous flow and perfect plastic. Newtonian flows, example water, shear stress directly proportional to rate of strain. So this is called as a Newtonian flow. Then structured soil, non-Newtonian flow, initial yield stress needed. That means it could able to offer some kind of a resistance up to certain load, and thereafter it suddenly deforms. So even if you don't apply any kind of a load. So this is the fundamental meaning of the slope stability. We introduce a factor called as a factor of safety. So normally that is defined as the force required or the force for resisting by the force by the driving force. That means The shear stress causes the slope failure. So therefore, this shear stress can be designated as the force for driving, while shear strength offers resistance against the shear stress. Therefore, shear strength can be designated as the resisting force. So if shear strength and shear stress both are equal, then you are on the verge of the slope failure. On the verge of the slope failure. So if shear strength is greater than the shear stress, then the slope is stable. But remember, if you take exactly one, this is always on the verge of failure. On the verge of failure. The reason is the shear strength is always constant. We can't increase any amount of the shear strength, but shear stress is a dynamic parameter. So this shear stress can vary depending upon the pore pressure condition or depending upon external perturbations like a liquefaction or earthquake. So that is the reason the factor of stability is not a single value. So it varies from one value to the another value depending upon the seasons. This is one of the fundamental reason. The slope which may appear stable in this year may fail in the next. So the basic reason is variation in the shear stress, not in the shear strength. So if factor of safety is greater than 1, it is stable. If it is 1, it is shear strength and decrease in the shear strength. So factors contributing to high shear strength, removal of lateral support. So this is most important for a geotechnical engineer. If anybody is asking some kind of a remediation action, sir, there is a slope failure, what could be the possible remediation action? So in terms of improving the shear strength or in terms of putting some another new structure where it impedes the causing of slope failure. So removal of lateral support, stream, water and glacial erosion, and there are some things. So you can go through it. Then overloading by weight of rain and snow fills. Oh, sorry, this is a high shear stress. Sorry, the factors contributing to high shear stress, which triggers the failure of the slope, removal of any lateral support. Okay, then overloading by rain and snow fills waste piles structures, transitory stresses, earthquakes, removal of underlying support, undercutting by running water, then lateral pressure. So water in interstices, freezing of water, increase of slope angle. So these are all causes which cause the slope unstable or which make the process of the shear stress a dynamic process. On the other hand, so there are other factors which will increase the shear strength or decrease the shear strength. The same thing. So composition and texture. So weak materials, example volcanic subs, sedimentary clays, loosely packed material, smooth grain shape, uniform grain shape, physico-chemical relationships, then effects of the pore water, then changes in the structure. Now just let me also make you to understand. When you talk about the slope stability, so in these two slides we have seen what could be the possible causes for increase in the shear stress. But at the same time, if the soil is not homogeneous, then there is a possibility of decrease of the shear strength even without increasing the shear stress. So these are the few causes. For example, the soil which is offering the shear strength is some kind of reactive material which reacts with any other chemical or water over the long term. Then there is going to be decrease in the shear strength. It may not be increase of a shear stress. Okay, so even if there is a decrease in the shear strength, in the factor of safety, or conversely, if there is a decrease in the shear strength of the soil itself, still there is a possibility of decrease in the factor of safety. So these are few causes for low and high shear stress and low shear strength. So then, so these are some information about the effect of the vegetation on slope stability, because you have been told vegetation is one of the best remedy for increasing the shear strength of the soil. So then you can see, so these are the few things you can understand about what it causes. Then let us come to the few modes of the slope failure. So this one is fall, next is topple, next is slide, next is spread, next is flow. So apart from these are belongs to only the soil, but apart from these kind of the modes of the slope failure, you can also encounter some other kinds of the mode failure when you talk about the or when you deal the rock mechanics. So I will explain about all these things, but uh, as far as geotechnical engineering concerned, so we always deal with only slide. So this is, we always deal with shear stress and shear strength of the soil mass. So these are the basic definitions of what is fall, what is topple. So this is a fall. Falls can happen in both rock as well as in soil. So this is called as a rock fall, but falls in rocks is quite prominent than in the soil. So this is in case of the soil. So this is soil fall. So very rapid. So undercut by the river. So the fall can happen. So because of the undercut, because of the erosion process, we can say. Okay. So in fact, if you recall, most of the landslide failures, so those failures may typically, a few of them may typically fall under the soil fail also, because this is what typically happens, the undercutting by the river flow. Then topples can occur in large bodies, maybe in the rock. Then debris topple. So debris topple in case of the clayey gravel and clean sand. This is rotational slump. Then slide. So these are translational, rotational, translational. Rotational means the shape of the failure plane is like curved. Translational means it is a failure plane, longitudinal. It is not a rotation. So this is planar rock block side, and this is rock slides, and this is a debris slide. Then lateral spreads. So this can happen on a very smooth or soft clays. Lateral spread can happen only on the soft clays. Okay, so these are all these fall under the category of the landslide or the slope instability. But when you try to determine the factor of safety, so when you in geotechnical engineering, when you read the geosynthetics, we normally address the lateral spreads. Provision of geosynthetics, one of the best way of avoiding the lateral spread. While in slides, when you are dealing with the slides, we talk about the rotation and we talk about the translational. So these are the few things we deal with in slope stability chapter. So this is the topple. So this is the fall. So this is the detachment of soil and the rock fragment that fall down a slope. So below figure, so you can see large rocks are falling from a greater heights to the lower height. So this is one of the example. So these are called as a rock falls. And this is a topple. So this is a forward rotation. Topple means there should be some kind of a rotation over the fixed place. So this is a forward rotation of soil or rock mass about an axis below the center of gravity of the mass being displaced. Here you can see how they are toppling one over the another. So this is a slide where the shear stress is greater than the shear strength. This is a flow. So flow normally occurs when the water content or the moisture content of the soil is significantly higher. We can say the water content is higher than the liquid limit. So this is a downward movement of soil mass similar to viscous fluid. But when soil has to be turned into a viscous mass, so its moisture content should be very high. And normally we also talk about in soil mechanics, basically two things. One is translational slides, next is rotational slides or slumps. So translational and rotational. So this is the fundamental distinction between the translational and rotational. In case of the rotational, the surface is a particular curve. Curve means it could be a circular curve or it could be a log spiral. Straight line dominates the translational failure. Here curve shape dominates the rotational slide. Otherwise there are small details, you can go through it. because you have already understood all about all these things during the undergraduation program. So I just try to address. So this is the best example for translational slides. So on Illy slope, you can see. So this is the exposed surface. If you look at the exposed surface, it is like a perfect horizontal. It's a perfect horizontal. So somewhere at the top there is a small again vertical cut, then followed by the movement. And this is also, this is rotational. So in case of the rotational, we could see formation of a particular curved shape. So this is rotational. You can see here, this is the best example depicting what is a rotational slide. So this is original shape and this is slumped one. So this is also rotational, and this is a rotational landslide. So you can see all curved surface. And this is landslide, and these are all, this is rotational landslide, and this is also rotational. Okay, so now let us try to understand the technical details about what is the factor of safety. So as I explained earlier, so factor of safety can be defined as it is a ratio of the shear stress, shear strength upon the shear stress. So tau F average shear strength of the soil mass, tau D average shear stress developed along the potential failure surface. So in order to make you understand, normally we try to determine the shear strength of the soil using the Mohr-Coulomb failure envelope, that is tau F is equal to C dash plus sigma dash tan pi dash. So where C dash is the cohesion and pi is the angle of internal friction and sigma is the normal force which is on the soil mass, and this is the shear strength of the soil. This is Mohr-Coulomb failure envelope. You can see this is the cohesion intercept, angle of internal friction. You can see this is the maximum shear strength. And when you try to impose any normal load, so you are obviously increasing the corresponding shear strength on the soil mass. So whenever the increase in the normal load reaches the maximum shear strength, then the failure is imminent. Here you can see you can increase the normal stress. The increase in normal strength causing the shear strength. So when this shear stress reaches the shear strength of the soil, so this is the formulas. So tau D, this is shear stress, C dash plus sigma dash tan pi. Often where C dash and pi dash are the cohesion and the angle of internal friction developing along the failure surface. So factor of safety is shear strength upon shear stress. Shear strength upon shear stress. But in geotechnical engineering, we normally deal with two varieties of the soils. One is cohesive soils, next is frictional soils. Or for the same shear strength of the soil, often the cohesion dominates the shear strength of the soil, or on the other hand, sometimes the friction dominates the shear strength of the soil. So accordingly, a factor of safety can be defined with respect to the cohesion or with respect to the frictional component. Just remember, we can have two independent factor of safety values, one corresponding to the cohesion component and another corresponding to the internal friction. We can have, although we normally take only one factor of safety, but you are allowed to take the factor of safety independently for the cohesion and independently for the frictional soils. So if you are defining the factor of safety with respect to only the cohesion, then this becomes so C dash by C, the cohesion, maximum cohesion developed by the cohesion developing because of the external load, that is normal load. Then similarly the factor of safety with respect to the friction, that is tan pi dash by tan pi d dash. So shear strength cos shear strength by shear stress. So when you say the factor of safety with respect to, if you assume that factor of safety with respect to cohesion is equivalent to factor of safety with respect to friction, so then you can normalize this one. C dash by CD dash is equal to tan pi dash by tan pi d dash, so that we can say whatever the factor of safety with respect to cohesion and factor of safety with respect to friction is almost equal. But although this is practically not possible, so this is useful when you want to understand the behavior of the cohesive soils independently and the frictional soils independently. So when the factor of safety is equals to 1, Fs is equals to 1, the slope is in a state of impending failure. If it is 1.5, it is stable. Okay, so I have taken small examples just to make you understand what is the importance of factor of safety against the cohesion and angle of internal friction. So please take out your notebooks and try to solve these problems. So just to get a fair understanding of the factor of safety determination. So these are the shear strength parameters of a soil given C dash is equal to 26. So calculate the factor of safety with respect to strength, with respect to cohesion, and with respect to friction. And the average intergranular pressure sigma dash on the failure surface is 102.5 kN per square meter. So just take pen and paper. So try to note down and try to solve this problem. Now let me address one of the most important thing. So when you look at this sum, see the soil which has been considered in this sum is remains same. The soil which has been considered in this sum is remains same. On that soil we determine the shear strength, and on that soil we determine the shear stress. C dash and C dash M, pi dash and pi dash M. Okay. So can anybody able to give a clear definition? What is the difference between C dash M, pi dash M? Looking at this problem, can anyone able to give a small explanation about what is the difference between C dash, pi dash, C dash M and pi dash M?
The C dash M and phi dash M are the mobilized parameters.
Yeah.
Which means that they are in kinematic friction zone.
They are in kinematic friction zone. Okay. So basically they are mobilized.
Yes, sir.
Mobilized cohesion and mobilized angle of internal friction. Very good. So why these values are less than C dash and pi dash?
Sir, because once the kinematic friction, first of all, kinematic friction will take place, so it will reach a static value. Then only C and phi will come into the picture.
Okay, but what is the fundamental distinction? See, that is okay. That is a mathematical analysis. So what is the meaning of this 26.7 kPa?
So this is the maximum cohesion that the soil has.
Okay, so this is the maximum cohesion that the soil is going to offer. Okay, so that means if cohesion exceeds 20 or if it reaches the 26.7, then there is a failure. All right.
Yes, sir.
Okay. So, but will it really reaches up to 26.7 or it can fail even before that?
Sir, the failure will start from the value of 17.8.
Yeah.
And it will fail till 26.7.
Okay, exactly. So just try to understand. Mobilized means the amount of the load required just to trigger the failure. That is called as a mobilized. Mobilized means who is going to get mobilized here? The soil. Okay. So until 17.8 kilopascals, nothing is going to happen inside the soil mass. Nothing is going, it is intact. No development of the failure plane or something. But when the shear stress is reaching to 12 degree in terms of the friction and 17.8 in terms of the cohesion. Then the particles starts just moving. The particles starts just moving. That is called as a mobilizing. Mobilization just starts. But when mobilization starts, so the values will not remain only at 17.8 and 12. They will increase. Okay, that means if the entire soil mass has to displaced from that particular location, the C value and pi value shall start from the 17.8 and should reach up to 26.7 and 15. Then only there is a complete dislocation of that particular soil mass. Okay, that means initially you need to understand at what cohesion and angle of internal friction the sliding gets just initiated. This is called as a incipient condition. So these values are called as a incipient conditions, means values which are just required to start the mobilization. So that is the meaning of mobilized value. Because everybody well aware of C dash and pi dash, because you brought the soil sample to the laboratory and you have conducted reaction the Mohr-Coulomb failure envelope, and from there you determine the C dash and pi dash value. But these values are at these values the sample has already failed. But the failure has started somewhere even before the values are reaching at C dash of 26.7 and 15. Okay, what is that starting point? Those starting points are 17.8 and 12. Okay, so this is what is the meaning of mobilized values. Now this is a very simple and straightforward problem. So the factor of safety with respect to shear strength, S is equal to C dash plus sigma dash tan pi. The shear stress, the shear strength of the soil is 54.2 kilonewton per square meter. Then the average value of the mobilized shear resistance is, try to use the C dash and the pi dash of mobilized values. So this is 39.6 kilopascal. So the factor of safety with respect to the strength, so which is nothing but shear strength divided by shear stress, 1.37. Now it is asked factor of safety with respect to only cohesion, that is 26.7 by 17.8, 1.5. With respect to the friction, so tan pi dash by tan pi dash m, so that is 1.26. So just see it. For a given soil, we got three variety of the factor of safety values. One is with respect to the strength, the next is with respect to the cohesion, and next is with respect to the friction. Okay, so but suppose if the frictional component is dominating in the soil, your factor of safety value is least. And suppose the factor of safety is dominated by the cohesion, the factor of safety is highest, and the combination is always in between. Just see it. With respect to cohesion is always highest, and with respect to not always, with respect to cohesion in this case is highest, and with respect to the cohesion is least, and the combination is in between. So this is another sum. Yeah.
Sir, you said that these mobilized cohesion are the starting values for the failure.
Yeah.
Sir, and so these will increase with time.
Yeah, they will increase with time. But it's
So,
not
so every slope must fail after some time, we can say.
Yeah, correct. Every slope must fail after some time. But
And
as
that
long,
time can be very long also.
yeah, very long. It could be 1 year, it could be 1 month, it could be 1 billion year, 1 billion year also.
Okay.
Suppose on that particular slope, if there was no external perturbation, if there was no movement of water, so just note down another sum. So the above example shows the factor of safety with respect to shear strength of 1.37, whereas the factor of safety with respect to cohesion and friction are different. So consider two extreme cases. So when the factor of safety with respect to cohesion is unity, and when the factor of safety with respect to friction is unity. So then you can determine, you can back calculate what could be the minimum factor of safety values with respect to the cohesion and with respect to the friction. Suppose if I take when the factor of safety with respect to cohesion is unity, so then what could be the overall factor of safety and what could be the factor of safety against the friction. So this can be determined. So here this is factor shear resistance is 39.6, so 39.6, and if you are assuming that case 1 where the factor of safety with respect to cohesion is unity, then we can determine the factor of safety with respect to the friction. Okay, and case 2, when the factor of safety with respect to the friction is unity, then what would be the value of the factor of safety with respect to the cohesion? So you take the shear stress, and with respect to friction is 1. So therefore, if it is 1, then what would be the value of the factor of safety with respect to the cohesion for the same shear strength. So these are increased value of the factor of safety. So the frictional factor of safety against friction increased up to 2.13, and with respect to cohesion it has increased up to 2.2.
Sir, among these three factors,
Yeah.
Which is the most relevant, as in for checking the stability, which factor should we consider?
There is nothing like that. Which one should consider? So this is for your basic understanding. In fact, when you determine the factor of safety, so you need to make all these trials. Suppose if I ignore the cohesion component, and what happens to the factor of safety if I ignore only the frictional component? Is dominating or causing the failure. Now when you assume FC is unity or Fy is unity, we are simply ignoring these factor of safety values. That means you are giving top priority to the frictional component. Then you are seeing that how much is improvement in the factor of safety. So there may be possibility of decrease also. If it is increasing, there is no problem. But if there is a decrease, then we will be in a trouble. So this should give a clear understanding about if I ignore one component, then what will happen to the factor of safety of the other component. Will it able to resist or will it not? Will it immediately cause the slope failure?
So we check the basically by different trials, we check the least possible factor.
Yes, least one. But this is very primitive, so we don't need to rely on all these things.
Sir,
Yeah.
Sir, you said that we can get C and phi by testing in lab. We get C and phi. How
Correct.
can we get CM and phi m? One process is stability number, Taylor's stability number.
No, we can't able to exactly determine the CM and pi m in the laboratory. Rather, we can interpret. See, for
Okay,
example,
sir.
in this sum,
Yes, sir.
we have a stipulated guidelines on, say, if you look at IS code, the IS code says the minimum factor of safety value with respect to the strength is 1.5. Okay.
Okay, sir.
With respect to strength is 1.5. Now, suppose if I substitute 1.5 equation, so can I back calculate the mobilized cohesion and mobilized angle of internal friction?
Yes, sir.
So that's what you need to do.
Okay, sir.
Rather, we can back calculate.
Okay, sir.
Okay. Okay. Once you are back calculated the C dash M and pi dash, Okay, then
Yes,
this
sir.
should give you a clear understanding about what should be the depth of surcharge load.
Okay, sir.
Okay, you got it? What should be
Yes,
the
sir.
depth of surcharge load?
Yes, sir.
Suppose if your depth of surcharge load is causing more C and more pi, it indicates that you are going to encounter the slow failure.
Yes, sir.
Sir,
Yeah.
sir, how that C value is increased from CM to C dash?
How it has increased?
Yes, sir.
See, for example, say this is a slope. Okay. So now this is causing the shear strength bottom. This soil mass is causing the shear strength,
Yes, sir.
and this weight of the soil mass is causing the shear stress.
Yes, sir.
Okay. So when it is moving downward, the resistance is offered in the upward direction.
Yes, sir.
So that means shear strength is in the opposite direction to the shear stress. Now, when this weight component is causing the shear stress, it is not an instantaneous process. You got it?
Okay. So it increases gradually.
It won't increase gradually. It's not like that. So there is some value of the shear stress already there once the entire construction is finished.
Okay.
Okay, but just imagine if the failure is happening during the construction, that means your shear stress is developing as you are progressing in terms of the normal stress application. What is the meaning of increase in W? You are increasing the normal stress component.
Yes, sir.
Okay, so without understanding about the normal stress component, if you keep on increasing or if you keep on putting the load, then this causes increase in the shear strength. At some point of time, something has to cause some kind of a destabilization or the failure, and that triggering point is only at a particular point where it just started mobilizing the soil mass. That mobilization is called as a mobilized angle. But okay, and once this has started, and the C value, pi value keeps on increases because the slope has to fail. If there was no increase of C dash pi dash, there was no failure. It was still at incipient condition only. Unless otherwise the C dash m pi dash m increases and reaches to C dash and pi dash, there was no failure. There was no failure. But it is about to fail. It is about to fail only. The triggering condition still exists. So when C dash m and pi dash m are increasing in a sense, suppose say you increased the normal load, then suddenly it increases. C dash m and pi dash m increases. Or that there was some earthquake which causes the lateral disturbance. That means increase in the C dash m and pi dash m. Or there was increase in the pore water pressure, or there was a sudden rapid drawdown condition. So these are the causes which increase the sigma dash and thereby which increase C dash m and pi dash m. Suppose if you are not increasing the sigma normal component, normal stress, then the same increase of C dash pi dash can happen because of increase of the pore water pressure or due to external perturbations such as earthquake.
Okay. So in that case, the C value is dependent on the normal stress.
Obviously,
Generally, if it is not for the shear strength.
your CSC triaxial element, you are applying only sigma 1 and sigma 3, and thereby you are determining the normal stress and shear stress.
Yes, sir.
Okay. It is nothing but super surcharge load only.
Yes, sir.
this is another problem. There is nothing great. So I will skip it out. Okay, so let me take it today. So the stability of infinite slopes. This is also very well known to everyone. So I don't take much time. But let me explain once, because many people, I don't know whether you were able to understand or not. So in fact, if it is on the blackboard, I used to draw everything, but I used to explain here, so I don't have such a chance. Now let us consider some or any infinite slope. So where the length of the plane is very long, where we don't know, it is an indefinite length. However, we know the formation of the soil on that form strata is very shallow, so which is designated as H. So H is the thickness of the soft soil layer. So when I say soft soil, instead of soft soil, try to understand this as a loose soil or the soil, and below is the hard strata, that is a rock. That is a rock. Okay, so where beta is angle made by this slope. Beta is angle made by this slope. And AB is a failure plane. So AB is the tentative failure plane. So it is presumed that along this failure plane, so the slope, the landslide is going to happen. Now take a small element. Take a small element, that is A, B, C, D. So whose horizontal length of the element is L? Whose horizontal length of the element is L? Okay. If horizontal length of AD is L, what would be the inclined length of AD? So this angle is beta and this length is L. So try to determine the inclined length of AD. Horizontal length is L. We can take sin pi or cos pi. So depending upon L cos beta. Okay. So if L is the horizontal length of AD and the inclined length of AD is L cos beta. Okay. Now, when I have taken this small element of A, B and CD, if you try to draw the free body diagram of this element, so first of all, the first is the weight of the element W. Okay, so the weight of the element is W. Then, so on either side of this element A, because and these normal forces are equal and opposite in magnitude and direction. So therefore, the element A, B, C, D is in equilibrium, so it doesn't have any kind of the movement. And we are not also considering any kind of the shear stresses, so no shear stresses are developing. That is an assumption. So first assumption is the normal forces are equal and opposite in direction, and therefore they are nullified and no shear stresses are acting. So all along the planes CD and AB. CD and AB. So therefore, what are the remaining the force components in the element is only the weight of the component. Only the weight of the element A, B and CD. A, B and CD. Now, this weight W, so which causes when it is moving in the horizontal direction or inclined direction, it develops or this causes the shear stress. This causes the shear stress. So this is normally we represent as the normal stress and shear stress. Normal stress and shear stress. The weight of the component is causing normal stress and shear stress with an inclination of beta, which is again equals to the slope angle to the beta. Okay, but this is this entire NA, TA and W. So in fact, NA and TA are the components of the W. NA and TA are the components of the W. This is what exactly you have done your triaxial testing. So what you have done there, you applied the sigma 1 and sigma 3 and you try to determine NA and TA. NA and TA. Okay, so this is normal stress and the shear stress. Now when this block is trying to slide all along the failure plane AB, the shear strength gets developed in the direction opposite to the W. Opposite to the W. So we can call R is the reaction. R is the reaction whose magnitude will be equal to the magnitude of the W. So we can assume that R is into the W at equilibrium. At equilibrium. Okay. So that this A, B, C, D will not further move. Now similarly, when there is a reaction R, so this also causes the normal stress and this opposite to the normal stress and shear stress caused by the W. Normal stress and shear stress caused by W. So is this part is clear?
Yes, sir.
Anybody has any question? Okay, now here how do you define the factor of safety based on this small diagram? Which component should be higher than which component so that there is no slow failure?
So TR should be greater than TN.
Yeah, TR should be greater than the TA. So TR can be designated as
shear strength,
and TA.
the shear stress.
Okay. So is it clear to everyone now? Okay. So TR is nothing but the shear strength and the TA is nothing but the shear stress. Now if I know W, how do you determine the W?
Sir, gamma into Z.
Gamma
Simple.
into volume.
Gamma into volume. See, if I know the area A, B, C, D, and I know the density of the soil mass, multiply density multiplied by the area, that will give the weight component. Weight component. Now, volume component, if you want, you take 1 meter of a length perpendicular to the screen or perpendicular to the diagram. So this is 1 meter. This is 1 meter. Since we always normally take for unit length, so we normally simply ignore multiplication of this 1 meter. So therefore we say W is nothing but, so gamma multiplied by area of A, B, C, D. A, B, C, D. Now how much is the area here?
H into L cos theta.
So H into L cos beta. Alright. Height, H is the height, and multiplied by L cos beta or L by cos beta?
Sir, I think L by cos.
By cos.
L by cos beta. So L by cos beta. So this is your W. Your W is nothing but now. So gamma H L divided by cos beta. Cos beta. Is true now? Any question? So anybody has any question? Now if I know the W, can I able to determine the NA and TA? Can I resolve W into NA component and TA component?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So NA is nothing but W.
Cos
Cos
beta.
beta.
So NA is nothing but W cos beta. TA is nothing but W sin beta.
W sin theta. Sin beta.
W sin beta. Okay. So now you get all the parameters. Okay, so this is how we can able to determine the shear stress parameters. This is as simple as possible, shear stress parameters. So based on this explanation, let me show all the simplifications so that you will not get any confusion. So this is the free body diagram. Weight of this component, volume of the soil multiplied by unit weight, that is gamma into L into H. Gamma LH cos beta, gamma LH cos beta, and TA, force parallel to the plane, that is gamma L into H into sin beta, gamma into L into H into sin beta. So this is these are the two forces which are, this TA is causing the shear stress within the soil mass, shear stress within the soil mass. Now in here we are dealing with only the forces and convert this into the stresses. Convert this into stresses. So stress is equal to force divided by the area. Convert the force into the stress. So sigma dash is nothing but NA by area of the base. NA by area of the base. So NA is gamma LH cos beta divided by the area. So here you need to multiply 1. Length, the 1 is in the perpendicular direction. The 1 in the perpendicular direction. So this is only the width, na, L by cos beta. And similarly here also you must multiply with 1. So then this becomes area. This is length multiplied by the width, 1. So your normal stress is nothing but gamma H. If you simplify, L will get cancelled out. So gamma H cos square beta. And the shear stress component, that is TA by area of the base. TA by area of the base. So that is gamma LH sin beta by L by cos beta. So this is gamma H sin beta into cos beta. Sin beta into cos beta.
So which dimension is L by cos beta in the figure?
L by cos beta is inclined length.
So is it L by cos beta or L cos beta? L into cos beta.
You try to calculate accordingly. Whatever the way you take it, doesn't matter.
Yes.
What it become. So if you are L by cos beta. I know horizontal, na? I know
Yes, it's
horizontal.
horizontal. Yes.
Yeah. So cos beta is nothing but abscissa by hypotenuse.
Yes, I got it.
Okay. Sin beta is opposite side by hypotenuse. So your W is nothing but R. So these are the effect normal stress and shear stress components determined from the weight of the soil sample. Weight of the soil sample. Similarly, you should also determine the almost same things, that is reaction components, the shear strength components. Shear strength components. TR is R sin beta, that is W sin beta, and NR is R cos beta, that is W cos beta. So W cos beta. So then for equilibrium, the shear stress that develops at the base of the element is equals to TR by area, that is shear strength, that is gamma H sin beta cos beta. But we know the shear strength equation. So tau D is nothing but C plus sigma tan pi. This is shear strength equation. So this is the shear strength equation. Okay. So this is the shear strength and this is the shear stress. These are all the shear stresses. and this is shear strength. So tau d is equal C dash plus sigma dash, your sigma dash is gamma h cos square beta, multiplied by tan pi dash. But tau d is calculated as gamma h cos beta sin beta, cos beta. So C dash is C dash d and gamma beta tan pi dash. Okay, so just try to rearrange the terminology. So into one particular thing. So that is C dash by gamma h is equals to sin beta cos beta minus cos square beta into tan pi dash d. So this can tan beta minus tan pi dash. Tan beta into tan pi dash.
Sir?
Yeah.
Sir, here all the parameters are drained, considered?
Yeah, drained. We are not considering the seepage. Effective. Okay, so let us look at this equation carefully. In this equation, beta is the slope angle. We can't able to change this value. This is a fixed. Okay. Then for a given soil, we can able to determine the cohesion component and the angle of internal friction component. Then density of the soil is known. So then we can able to determine what should be the critical height. Okay, so if I know the beta angle and if I know the C dash and pi dash angle, I can able to determine the critical height. So behind which there is a slope failure of infinite slope. But this is already under drained condition or effective stress condition where there was no water at all. Okay, suppose if you want to determine the existing slope whether it is stable or not, where h is known, so then you try to determine C dash value and pi dash value and try to compare whether right side is equivalent to the left side. So if they are reasonably high, then you can say that the existing slope is same. If not, then there is a possibility of the development of failure. So the factor of safety with respect to the strength has been defined as, if you remember earlier, so with respect to the strength, tan pi dash d is equal to tan pi by tan pi C dash d, C dash by C dash d. So substituting the above into below equation, this is simple. So now because we arrived at C dash d by gamma h is equal to sin beta cos beta minus cos square beta. So for that, you try to substitute the factor of safety Fs values in terms of the cohesion and in terms of the angle of internal friction. So C dash d can be written as C dash by the factor of safety. Similarly, pi dash d can be written as tan pi by factor of safety. So substitute everything here. Then rearrange. So bring the factor of safety onto one side. So this is how you will get the equation. So C dash is equals to gamma h by cos square beta into tan beta plus tan pi dash by tan beta. Now if you look at this equation carefully, so this term belongs to the cohesion component and this term belongs to the frictional component. Then accordingly, so if you superimpose or if you try to interpret the information from the Mohr-Coulomb failure envelope, so this is a Mohr-Coulomb failure envelope. So this line belongs to the frictional component where it is passing through the horizon. Then this line belongs to C5 soil. So the C5 soil. Then accordingly you can determine what happens to the factor of safety value. So as you are increasing the slope, so from this equation you can understand that suppose if you look at this one, we can understand that if beta is less than pi, the slope is stable. Slope is stable. But this is valid only in case of granular soil. If you put C is equals to 0, then what you get is tan pi dash by tan beta. So when the slope becomes the angle of internal friction, then your factor of safety is 1. So factor of safety is 1. That is Fs is equal to tan pi dash by tan beta. The frictional angle is within the slope angle, the slope is stable, but on the verge of failure. So if you look at this graph carefully, we can see at some point, that is point AB, the response of the frictional material is equivalent to the response of the C-pi soil. Or you can understand it another way. So the behavior of C5 soil is at some point is equivalent to the behavior of the frictional material. This is what we understood from the triaxial testing. What happens when you are conducting the UU test, CU test, and CD test? How the C pi component is becoming only the pi component domination. Okay, so suppose if you want to further understand, in case of the C5 soil, say you could able to put large small amount of you can say, yeah, you can put small amount of normal load on C5 soil compared to only the frictional material, under the frictional material. Suppose if you want to interpret what is the meaning of DCE, CE indicates the amount of the normal stress on the frictional material. DE indicates the amount of normal stress on C5 soil. Okay, so this is just, suppose if we assume there is a critical equilibrium occurs, at that condition the factor of safety is 1, then we can able to determine what is the critical height of or the critical depth of the soil mass, so which can able to sustain so without undergoing the failure. So H critical is C dash by gamma into 1 by cos square beta into tan beta minus so tan pi. Okay, you try to understand everything very carefully. If you have any question, please ask me. Interfere me and keep on asking. So this is I explained already. So C dash by gamma H. Yeah, now here comes, so we arrived at the equation of C dash D by gamma H is equal to sin beta cos beta minus cos square beta into tan beta. So here the left side term, so that is the term C dash by gamma H is a dimensionless expression called as a stability number. So this C dash by gamma H is termed so that the NS can be correlated to the internal friction of the angle as well as the slope of the angle. Now what they have done is, if the factor of safety with respect to friction is unity, the stability number with respect to the cohesion may be written as this one. So because if you look at the previous slide, C dash D is equals to C dash by factor of safety, and tan pi dash D is equals to tan pi by factor of safety. So when you are assuming the friction is unity, then the stability number can be expressed in terms of the cohesion, so by this form. So C dash D is equal to C dash by factor of safety, into gamma H into cos square beta. Then similarly, where C dash M is equals to C dash by the factor of safety. So similarly, NS is equal to C dash by FC into gamma H or C dash by gamma HC. So if you, where C indicates the critical height, at which the FC is unity. So at a critical height, the factor of safety with respect to the cohesion and the factor of safety with respect to height are same. at critical height, the factor of safety with respect to the cohesion and with respect to height both are same. So this is another interpretation that can be made from the derivations. So this is if you are assuming the study seepage, and if you try to draw the free body diagram, try to solve everything, and this is what is the final equation that you will get. Factor of safety is equals to C dash by gamma sat into H cos beta tan beta plus, if you remember earlier, this was tan pi dash by tan beta. Let us look at, if you look at earlier, when there was no seepage, the equation for factor of safety is C dash by gamma into H cos square beta tan beta plus tan pi dash by tan beta. Now what if the entire slope is under steady state seepage condition? Your bottom term, the gamma, now became gamma saturated. Now there are two additional terms which are coming into the picture, that is gamma dash and gamma sat. Gamma dash is nothing but the submerged unit weight of the soil mass, and gamma sat is the saturated density of the soil mass. You can see the ratio of gamma dash by gamma sat is always less than unity. Because submerged weight is always less than the 9. So gamma dash is always less than gamma sat. So this component, there is a tremendous decrease in the component of the frictional, but that is not because of the decrease in the pi dash, but decrease in the density value. While in the cohesion component also, the weight of the soil mass getting increased, and thereby the factor of safety is getting decreased. So again here also, if you deal with only the cohesion soil, when there is a steady state seepage condition, your factor of safety value is going to decrease. So because of increase in the weight of the soil mass. Well, suppose if you take only the frictional component, still there is a decrease in the factor of safety value, because so you are taking the lesser unit weight on the numerator than the denominator. So this is under fully submerged condition. You can see, in fact, just a rearrangement. Suppose if you look at normal stress, sigma dash is equal to gamma h into cos square beta. So this is under submerged condition. So this will become gamma submerged. Now gamma, it's not bulk, it is gamma submerged. And shear stress, so this is gamma sat into h cos beta. So this is how your equation is becoming gamma dash by gamma sat. So substitute, arrange everything. If you have any doubt regarding the derivation, so then this is the small derivation. Okay, so just try to note down the small sum. So for the infinite slope with a steady state seepage shown in figure 15.9, determine the factor of safety against the sliding along the soil rock. So this is a rock and this is the soil. The thickness of the soil is 6 meter, and it is completely submerged. The groundwater table is on the surface. So there is a seepage force. Gamma sat is 17.8 kilonewton per cubic meter. C dash is 10 kilonewton per square meter. Pi dash is 20 degree. And slope angle is 15 degree. The factor of safety against sliding along the soil rock interface. The height h, that will give a factor of safety fs of 2 against sliding along the soil rock interface. So component A is part A of the sum is, if height of the soil is 6 meter, what is the value of the factor of safety? The second, if the factor of safety is 2, then what should be the height of the, or what should be the thickness of the soil layer on the rock?
Sir,
Yeah.
is beta 15 or 25?
Let me check it once. Beta is 15, not 25. It's bottom angle. Okay, so this is the solution. The equation for the factor of safety under steady state CPS condition is C dash by gamma sat cos square beta tan beta plus gamma dash by gamma sat into tan pi dash by tan beta. Tan pi dash by tan beta. So gamma given is 17.8 kilonewton per cubic meter, and gamma submerged is gamma sat minus gamma W. So this is 7.99 kilonewton. So the factor of safety is equals to, so C dash given is 10 kilopascals, 10 by 17.8 into 6, that is height of the soil layer, then cos square beta, then so tan beta plus gamma dash by gamma sat into tan pi dash by tan 15. So this is 0.375 plus 0.61, 0.985. So 0.985. Okay, since the factor of safety is less than 1, so there is a failure. So there is a failure. Now let me ask a couple of questions here so that remaining things also clear to you. Now here the factor of safety is less than 1. So in how many ways I can increase the factor of safety to above 1?
So decreasing beta.
So by reducing height.
Decreasing beta, reducing height.
So by
then
lowering water table.
Yes, lowering water table.
By lowering water table. Then so you can increase the cohesion component, you can increase the angle of internal friction component. If you increase from 10 to 20, your factor of safety value increases. If you increase 20 to 30, your factor of safety value also increases. Okay, but although there are several parameters which are influencing the factor of safety value, but all do not be having the same fundamental understanding for a geotechnical engineer. Although the height is influenced, the seepage condition is influencing, the slope is influencing, C dash and pi dash, everything is influencing, but the degree of intensity with which they are influencing the factor of safety will not remain same. Will not remain same. What I do is I will give a small assignment for you for a clarity understanding. So among these five parameters, you try to keep on giving the degree of intensity, which is the most important and which is the most least important. Okay, so you come up with your own solution. You come up with your own solution. Among these five parameters, which should be accorded topmost priority and which should be accorded the least priority. Okay, in fact, you can attempt this sum in 2 to 3 ways. First, technical performance. Next, cost economics. I hope so you understood the question. So take it as an assignment. Among these 5 parameters, the first thing is, so which parameter should be accorded highest importance? You write in ascending or descending order. The second is, when you account for the technical performance and you try to arrange them ascending or descending order, and when you try to take into account for the cost economics, that which parameter from ascending to descending in terms of the technical evaluation, in terms of the cost economics. Okay, so the part B of the question is, if the factor of safety is 2, what should be the minimum height of the soil, or what should be the minimum thickness of a soil under same steady state seepage condition? Fs is equals to C dash by gamma sat into H cos square beta tan gamma dash by gamma sat into tan pi dash by tan beta. So since Fs has been given as a 2, only height is known and remaining all parameters are same. So substitute everything and try to recalculate the height of the slope. So which is calculated as 1.62 meters. 1.62 meter. So see the difference. When the height was 6 meter, the factor of safety was 0.98. When height was decreased to 1.62 meter, and your factor of safety was increased to 2. So that is the forward calculation and the backward calculation. So now suppose for an infinite slope, if the IS code is stipulating that your factor of minimum factor of safety value is say 1.5, then again you can calculate what should be the minimum height of the soil so that it is stable and will not fail. Okay, so this is how you need to understand when you solve different problems. So forward and backward calculation. So this is another sum. So find the factor of safety of a slope of infinite extent having a slope angle 25 degree. The slope is made of cohesionless soil. So with pi is equals 30 degree. So straightforward problem. There is nothing great. So the slope angle is 25 and internal friction of the soil is 30 degree. So since the soil is a cohesionless soil, the first term becomes 0 as C is 0. The first term is 0. So the remaining is only the second term. So the factor of safety is nothing but tan pi dash by tan beta. So beta is equal to 30 and tan 30 is equals to tan 25. So this is 1.238. Okay, just imagine what if pi dash is equals to beta. If the angle of internal friction becomes the slope angle, then what you get is unity value. The unity. Okay. So note down another sum. Analyze the slope of, so this is example, analyze the slope of, if it is made of clay having C dash 30 kilopascals, pi dash 20 degree, and E 0.65 and GS 2.7, and under the following condition. When the soil is dry, when the water seeps parallel to the surface, and when the slope is submerged. So here you are asked to determine the height of the slope. So under three different conditions. So based on the given data, try to calculate gamma D, dry density, saturated density, and submerged density. So gamma D, so gamma by 1 plus E, G into gamma W, G plus SR into gamma W by 1 plus E, where SR is, so this is dry condition, SR is 0, no degree of saturation. Then gamma sat, G plus E by 1 plus E into gamma W. Then gamma submerged, so gamma sat minus gamma W. So under dry condition, so since you are asked to determine the critical height, so the factor of safety is obviously unity. So therefore the equation can be written as C dash by gamma D into Hc into cos square beta into tan beta minus tan pi dash. So the critical height at C is equal to C dash by gamma D into Ns. So then the critical height is 22.25 meter. So in fact the same problem can be solved using the stability charts also. So when you talk about the stability number, so there are different charts available. If the charts are given, you can either solve by charts also. So there is no issue. Or analytically you can use all the equations. So this is under dry condition, and this is when seepage is parallel to the surface of the slope. So this is the equation. C dash by gamma saturated into Hc is equals to cos square beta into tan pi minus tan beta minus gamma dash by gamma sat into tan beta. So this is Ns value, the stability number value. Then substitute here, critical height is equal to C dash by gamma sat into Ns. Then you will get 6.51 meter. Then this is for slope. submerged slope. When it is fully submerged condition, so gamma will become gamma submerged. Gamma submerged. So the critical height is 35.4 meter. So again remember, so when I talk about the critical height of the slope, the factor of safety is unity. So whether it is mentioned in the problem or not, you have to understand the critical height is only possible when the factor of safety is unity. Okay. So
Sir,
yeah.
sir, in this problem, we can find that for the submerged slope, the critical height is maximum.
Correct.
So why this is coming maximum in? It will come in. It will come maximum for all the case, or just in this case particular it is coming.
No, in every case. See, now let us try to understand. See, for example, when the slope is dry, there was no movement of the water. So your critical height is 22.25 meter. Okay. When I say seep is parallel to the surface, there is some additional force acting in one particular direction. So because of this seepage force, so the height is coming out to be minimum. In third condition, there was no seepage at all. It is completely submerged. So seepage means when water is flowing within the soil sample, it causes a force called as a seepage force. Okay, that is against the gravitational force. In fact, it is not in the direction of the gravitational force. So therefore, when there is a seepage force, it is gravity plus seepage together. So together will weaken the slope. That is the reason you are getting the least height. But when I talk about the submerged slope, there was no movement of water at all. The entire slope is under the water. So the water weight itself is acting in a positive direction. Okay. So because of this additional weight of the water, which is again adding to the weight of the soil sample, but not in a way the seepage is happening. In case of the seepage, it is happening in a negative way, while in case of the submerged slope, it acts in a positive way. So because of this positive way, so the height of the slope is under submerged condition can be as max as possible. In fact, higher than the dry condition. And this is valid for any in general. Under all submerged conditions, you may go for highest amount of the slope. Sorry, highest amount of the thickness of the soil layer.
So, sir, slope stability is not related to the effective stress.
Under submerged condition, you can't talk about effective or total. Na? See, it's no more drained condition.
Yes, sir, no drainage.
Yeah.
So what we can say that water acts as a surcharge to the soil.
Yeah, it is acting as surcharge, but in a positive way. Surcharge means you can understand in a different way, but in a positive way.
Yes.
It is giving some kind of a stability. What you can see, if you can able to draw a picture, say this is the slope, say this is water level, and say when slope is trying to move in this direction, it is going to provide resistance in opposite direction. This is under submerged condition. Okay, suppose in seepage condition, so this is also seepage direction and this is also gravity direction. So because of this additional component, the height required is minimum. Okay, but in submerged condition, as you can see here, trying to come down, the water weight offers some kind of the resistance. Because of this resistance, so we can go for large thickness of the soil. Is it clear now? What is the meaning of positive and negative?
Yes, sir. Yes, sir.
Yeah. So I will stop it here. Maybe tomorrow I can discuss about Kalman's method and other methods.